Hello, this lesson looks at the electromagnetic spectrum, what it is, and the properties of the waves that make up the spectrum. The material covered in this lesson is relevant for both the triple physics course and also the combined science course. Usually at the start of this lesson, I get my class to complete a short practical. I ask them to shine a ray of white light through a triangular prism. We're now going to have a look at what happens. The results here aren't a surprise. We get the white light splitting into the visible spectrum, so the 7 colours of the rainbow: red, orange, yellow, green, blue, indigo and violet. What's important to note when you draw out this diagram is that the ray of light comes in and bends downwards as it goes through the top of the prism, and again as it comes out. We should never see anything that looks like this, because that would be completely the wrong direction. You'll notice that everything has turned down in this direction. So the obvious question is, why does the prism cause the white light to be split into the colours of the rainbow? How does it split the light into that visible spectrum? The answer is refraction. On the slide here, you'll see that I've homed right in on that top bit of the triangular prism. We had the white light entering the block on the left. And as you can see, I've drawn in a normal line, in a black dotted line there. Remember, the word normal means at 90 degrees. So therefore, this normal line is at 90 degrees to the surface of the prism. Now, normally the light should have continued off in roughly this sort of direction here. But as you can see, it's bent towards the normal. And we know that as light travels into something more dense, it bends towards the normal. As the light comes out of the prism at the other end, you can see again I've constructed another normal at 90 degrees to the boundary. Normally we'd expect the light to continue off in the same direction, but as you can see this time it's actually bent away from the normal. And as we know, when light travels from something more dense to less dense, it always travels away from the normal. So in summary, the light is refracted as it enters and as it leaves the prism, which means that the speed changes, and because it hits at an angle, so does the direction. The different colours of light have different frequencies, and we'll have a look at that a little bit more in a moment. The different frequencies are refracted by different amounts. What that means is that they are bent, or the direction changes by different amounts, so the colours emerge at different angles. At this point, if you haven't already watched the suggested video clips or had a look at the suggested websites, I suggest you pause the video and go and have a look at them. They're going to go into some information about the electromagnetic spectrum that I won't cover in this video because they'll do it a lot better. So if you haven't, pause the video now and go and have a look. You should have seen that the visible light spectrum that we saw emerging from the prism is just one small part of the larger electromagnetic spectrum. We place visible light at the centre, and that's the bit that we see and detect with our eyes. As we move in this direction to the right, the wavelengths of these waves are getting longer. So by the time we're down here at radio waves, they can be kilometres long. Typical wavelengths of light, as you can see, are in the hundreds of nanometers, and don't forget, nano means times 10 to the minus 9. As we head off in the other direction to the left here, these waves are getting shorter and shorter and shorter, so the wavelength is getting smaller and smaller and smaller. By the time we're into the UV spectrum, we're on 10 to the minus 8 meters. As we keep going down, you see that the gamma rays get smaller and smaller and smaller until we're down to the size of an atom, or even a nucleus of an atom and smaller. Now, if you're doing the homework, you should have worksheet 3.1, and I'd like you to fill that in now, please. I'd also like to suggest that you write in the wavelengths of each part of the electromagnetic spectrum. You would be expected to know this for an exam. Now, as well as knowing which waves are in the electromagnetic spectrum and their wavelengths, there are also some key facts that you must know about the electromagnetic spectrum. The first one is that all of these waves are transverse, and this is a word that we learned in a previous lesson. Remember, it means that the oscillations are at right angles to the direction of travel. Electromagnetic waves can therefore travel in a vacuum, unlike longitudinal waves which need to have particles. So electromagnetic waves can travel through the vacuum of space. That's obviously how light rays get from the sun to us. All electromagnetic waves travel at the speed of light. Now we know that this light travels at the speed of light, that's obvious, that's what the name means, but actually every single wave on that electromagnetic spectrum travels at the speed of light. That includes the gamma rays, the X-rays, the radio waves and so on. We're going to have another look at this in a moment, but it's really important to remember that like light, all electromagnetic waves can be reflected and can be refracted. That's why we look at these properties before we come to the electromagnetic spectrum. So the only difference between the waves in the electromagnetic spectrum is how their frequency changes and therefore wavelength, because obviously the shorter the wavelength, the higher the frequency. So at this point, I'd like you to pause the video, have a quick look at these questions and decide whether they are true or false. And in a moment we'll come back and we'll have a look at the answers. So here are the answers, and hopefully you got all of them right. So as we've just seen, all the waves on the electromagnetic spectrum can be reflected and refracted. So at this point, I would just like to recap those two things from a previous lesson before we move on. So this is the diagram we looked at showing reflection. As we can see, the angle of incidence equals the angle of reflection, and we're measuring those angles from that normal line at 90 degrees to the mirror. We've also seen that we can represent reflection using both the ray diagram we just looked at and also a wavefront diagram. And a quick reminder that these wavefronts are drawn at 90 degrees to the ray. And this is as if we're looking down on the wave from above and just seeing the peaks of those waves. So this is an example of a wavefront diagram for reflection. As we remember then, refraction is what happens when a wave moves into a material of a different density. And we know that its velocity will change. It will slow down if it goes into a more dense material, or speed up if it comes out into a less dense material. We also know that if the wave hits the boundary at an angle, that means at an angle to the normal, then the wave also changes direction. So this diagram shows the ray diagram for refraction. As the light enters the block, going from a less dense to a more dense material, it bends towards the normal. And as it comes out of the glass block, going from a more dense to a less dense material, it bends away from the normal. And as with the reflection diagram, we can also do both a ray and a wavefront diagram for refraction. As you can see on the right, as the light enters the block, it bends towards the normal, and so we see the direction of those wavefronts change. We also see the wavefronts getting closer together. The wavelength is smaller, and that's because the light has slowed down. And so from our wave equation, v equals f times lambda, if the velocity gets lower, so does the wavelength. So let's have a look at a practical application of what we've just learned. In the diagram, wave L is used to send a signal to a satellite. The first question is, which part of the spectrum does wave L belong to? Well, wave L is going to be a microwave because it's microwaves that we use to send signals to satellites. The second part asks what name is given to the process that occurs as wave L passes into the ionosphere. And so we're looking at this point here as it goes into the ionosphere. Well, if you have a look at what's happening, it's changing direction. And we know that the process which involves a ray or a wave changing direction is refraction. So as the microwave passes into the ionosphere, it's going to change its speed and it's going to change its direction. It's being refracted. Wave M is going to be reflected by the ionosphere. This is probably a radio wave. Radio waves don't pass through the ionosphere, they actually reflect off of it. So they've asked here, where would you draw the path of wave M to make it reach the receiver? So you might want to pause the video for a moment and have a think about your answer before we show the answer on the next slide. So we know that wave M, the radio wave, is reflected from the ionosphere. So we need to draw a diagram showing reflection. Now, in order to get full marks and to make sure that this diagram is accurate, you'll notice that in here we've included the normal line. And that, remember, is the line which is at 90 degrees to the boundary. And that's the boundary between the air and the ionosphere above it. You'll also see that we've made sure that the angle of incidence equals the angle of reflection. Now, in real life, if you were sketching this diagram on an exam, for example, as long as it looks about the same, then that's good enough. They're not going to expect you to get out your protractor. But it should be clear that those two angles are supposed to be the same. So at this point, I'd like you to pause the video and see if you can work out what the missing words are in this close activity. So here are the answers. When a wave meets a boundary between two media of different densities, and that's the key idea that we've looked at all the way through here. It's when a ray of light or a wave is trying to pass from one material to another one and the density is different, then something happens. Now it could be absorbed, reflected or transmitted. The absorption idea we look at again in a little bit more detail, particularly those of you doing the triple science. But we do know if it's a very sharp change in density, the wave may well be reflected like light from a mirror. It may be transmitted, and as we've already seen, if it's transmitted, we're talking about it being refracted. And if it hits the boundary at an angle, it will change direction as well as changing speed. So that's it for this lesson. Next time we'll be looking at the uses and dangers of each of the electromagnetic waves.